Alright, so now let's take a look at problem 5. So to construct the snowflake curve, start with an equilateral triangle, so all the sides are the same, with sides of length 1. And then step 1 in the construction is to divide each side into 3 equal parts, and then basically construct an equilateral triangle on the middle part, then delete the middle part as in this figure. So step 1 is to divide each side into 3 parts, and then construct an another equilateral triangle in the middle part and delete it. So in other words, so we separate this into 3 parts, draw a triangle, and then delete this part, and we're gonna be left with this. And do that for all 3. 1, 2, 3. So there's 3 there. So we divide those all in the middle. And step 2 is to repeat step 1 for each side of the resulting polygon. This process is repeated at each succeeding step. So initially we had 1 triangle, then we had to make 3 more on it. So 1, 2, 3. And now each one of these, we're going to make 1, 2, then make 1, 2, and then add another one here and here, here, and so on. So let's take a look at how this one is. So remember, this was that earlier triangle. This is the earlier triangle, but now we added 2 onto it. Onto each one of these segments here. But now this one, because you have another one here, here, so you're adding 2 on every single one there. It's just fascinating stuff. So it looks like that, and then you keep doing that again onto this, onto this, onto this, and then you become this. So yes, you can see how it looks like a snowflake now. So the snowflake curve, is the curve that results from repeating this process indefinitely. So you keep going on like a giant fractal. So now we're asked for question A. Let Sn, Ln, and Pn represent the number of sides, the length of the side, and the total length of the nth approximating curve, the curve obtained after n steps of the construction, respectively. And then it says, find formulas for Sn, the number of sides, Ln, the length of a side, and Pn, which is the total length of that curve. And notice here, every single one of these is exact same lengths. So we have exact same lengths on everywhere, even these all become exact same. This exact same. This is dividing it in thirds there, and these are all the same size. So it's always equilateral triangles everywhere. So, and then part B says, show that Pn approaches infinity, so the total length Pn approaches infinity as n approaches infinity. And then C, sum an infinite series to find the area enclosed by the snowflake curve. And then it says, note parts B and C show that the snowflake curve is infinitely long, but encloses a finite area. Fascinating stuff. Alright, so now let's take a look at the solution. So solution to part A. At each stage, each side is replaced by 4 shorter sides, each of length 1/3 of the side length of the preceding stage. And we can see this, but let's just draw our triangle like this, our equilateral triangle. I'm going to write it like this. And then the first one here, I'm going to cut this up like this. We'll do this actually twice here. So I'm going to cut this up right there. So initially we had side length L, and then we have divided into 3. So this can be L/3. This is going to be L/3 like that. And then we're going to have a triangle like this. And these are all exact same length. So instead of having one giant length one, we're going to have 1, 2, 3, 4. So this one is 1 and is replaced by 4 shorter sides. And these are all equilaterals. This is going to be side L/3. And this is going to be L/3. And this is going to be L/3. And so this side is it goes from 1 side to 4, and each one of them is a third shorter. So now, and you'll see this pattern keeps going on even if we do another one. So let's do another one right here. So if we have right here, and then split this in half. So this is L3. These are equilateral, and then you're dividing this by 3. So then this is going to be L/9. And they're all equilateral, so this is also L/9. And so it goes from one side here, one small side, it goes to 1, 2, 3, 4. And then again, there's another L/9, because they're all equilateral triangles. Like that. Alright, so now writing S0, And L0 for the number of sides and length of the side of the initial triangle, we can generate the table below. And also just note on solution A, we're just asked to find the formulas for the number of sides, the length, and the total length of the curve. So what we'll do is start S0 and L0 for the number of sides at the beginning. So let's write this down. So the first one, we have just a regular triangle, just one triangle, equilateral triangle. We have 1, 2, 3 sides. So our S0 is equal to 3 sides, and our length L0 is equal to 1. So they're all length of 1. So that's what we start off with right here, all length of 1. So that was the 0th one, and now the step 1. Yeah, so we'll put a 0. This is the 0th, so start off at 0. Now we go to the step 1, and we go from right here. So we split this up like this. And then this goes like that, and like this. So each one of them is split, and goes like that. Actually no, it keeps going. Actually, actually it's like this, and that is our 12-sided triangle. The 6-pointed triangle. The 6-pointed star. Actually, yeah. So 1, 2, 3, and there's 3 at the bottom. So let's count the number of sides. We have 1, 2, 3. 4. So those one side becomes 4, and each one of these does that as well. So we just multiply by 4. So S1 equals to 3 times it by 4. So we multiply that 4 3 times, and the length is going to be half. So a third. Each one of them is a third. So L1 equals to 1 over 3. And then step 2, we do the same thing, and what we'll get is, each one of these sides becomes 4. So this one here, I'm going to write this like this. So this one right here, write it over here. So it's going to go like this, and it becomes a triangle. It becomes 4 sides, like this. And then this other one becomes 4. Then this other one becomes 4. Oops, let's do this again. This becomes, and then this goes like that. And this one here goes to 4, like that. Now let's erase this arrow. So notice here, this becomes 4. This becomes right here is a 4. Each time there's a point, there's 4 sides, and there's another 4 right here. So there's 4 of those, and I'm not gonna. Then you just multiply it by 3 on each side. So this one, then you can do that same thing on here and here. So this multiplied by 3. So in other words, we're gonna get S2 is equal to 3, and this is 4 times 4. So it's 4 times 4. That's just 4 squared. And then L1 is equal to 1 over 9, or 1 over 3 squared. So each time it's half of the previous one. So 1 over L squared, and it keeps going on and on. And then just put dot, 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 and then this keeps going on, dot, dot, dot. So the nth construction, we get Sn is equal to 3 times 4 to the n, then Ln is equal to 1 over 3 to the n, like that. So in other words, we got the number of sides and the length, and then we could just find the total side length, the total perimeter around it. So multiplying the side length with the number of sides, we get the total length of the perimeter at the nth stage of construction. Or yes, we get that is, I'll remove this is, but just get the nth stage. So Pn is equal to the total number of sides times the length of each side, which equals to, this can be 3 times 4n, times it by 1 over 3n. And combine those powers there, so this is 3 times 4 over 3 power of n, like that. So that is our total length. So we have answered question A. And let's look at question B now. So that's question A. And now question B, so that's question A, find formulas for them, so we found them all. And question B says, show that P sub n goes to infinity as n goes to infinity. Alright, so let's look at solution to B. So taking the limit of the perimeter length, we get, and let's write this limit as n approaches infinity of Pn. This equals to limit as n approaches infinity of 3 times 4 over 3n. So in other words, this just goes to, infinity, because what we get is a 3 times 4 over 3 infinity. This is going to 3 times infinity, it's just infinity. There it goes to infinity. So it's equals to infinity, and this is since 4 over 3 is greater than 1. And yeah, that's also similar to that earlier limit we went over. So because it's greater than 1, it goes to infinity as you take it to the power of infinity. So yeah, so that's what we have. All right, so that's infinity, and now let's take a look at solution to C. So part C, let's see what it was. So C, sum an infinite series to find the area enclosed by the snowflake curve. So find the actual area there. So let's take a look here. So solution to C, the area of each of the small triangles added at a given stage is 1/9. So that's a key one. I'm just going to bold up. Of the area of the triangle added at the preceding stage. And just to illustrate this, so let's say we have an equilateral triangle like this, and length is, and it's all, so the base is B, like that, and then the height here, I'll just back and back. Yeah, let's write this better here. So let's say the height is, here is a right angle, and this is all lengths B, and then the height is H, and let's say you had an angle here is theta, like that. So the area, recall the area of a triangle is just base times height divided by 2. And now what are right here, we could write the sine, we could write the H right here. So we want to solve for H. So we could write recall sine is equal to opposite over hypotenuse. That just equals to H over B. H over B, so move it around. So H is equal to sine, just move this over to that side, sine theta times H. Sine theta times B. I'll put this here. B times sine theta. So throw that inside, and we're going to get a B times B sine theta, like that, all divided by 2. And then just square that. This equals to B squared 2 times by sine theta. So that is what the area is for this triangle. I'm just going to bold this. So that's for any given triangle like that. But in fact, we're not just dealing with just any triangle. This is an equilateral triangle, so this is going to be pi over 3 actually. So that's just pi over 3. I'll just put this like this instead of actually solving it. Pi over 3. So all of these are pi over 3. And they're all equilateral triangles. Alright, so we have that. So for so now for the next triangle after that, thus for length of or better yet, just write for side length, and then let's say we have a third of that. So for side length B over 3, then the area is equal to, well, we already know because they're all equilateral triangles. So this is going to be this area, but then we'll replace B with B over 3. So B over 3 squared over 2. And then times it by sine, times it by sine pi over 3. Like that. So this just equals to, well, equals to, this is 3 over there. I'm just going to square that. So this is going to be equals to 1 over 3 squared times it by B squared over 2 sine pi over 3. And so this is the previous one. Oh, this whole thing is a previous length. Yeah, so I'll just write this as A1, and I'll call this A2. This is A1 then. So the previous one, so A2 is equal to 1 over 9 times it by A1. So it's 1/9 of the previous one. And we can bold that here, or just circle it. So there it is. At any given stage, it is 1/9 of the area of the triangle added the previous preceding stage. Alright, so let A be the area of the original triangle. Yeah, so then the area AN of each of the small triangles added at stage N is, and let's just write it down. So let's say the 0th one we have A is the area. Then the A1 is equal to a times it by 1 over 9. And then a2 is equal to a 1 over 9 times it by 1 over 9. Or just write this as a1 times 1 over 9, which is equals to a 9 squared. And then dot dot dot, just for completeness, it goes an equals to a divided by 9 to the power of n. So notice when a2 is just a divided by 9 power 2, a1 is a times 1 divided by 9 to the power of 1. I mean, times it by 1 divided by 9 to the power of 1. So that is what our an is. Alright, so now since a small triangle is added to each side at every stage, it follows that the total area an added to the figure at the nth stage is, so this is the extra area. So we start off from the beginning, so let's say we start off here, and then we're going to add an extra, so this is a, we're going to add an extra a over 9, an extra a over 9. An extra a over 9 at each side. So initially there's 3, now we're adding 3 at each side. So 1 at each side. A over 9. So we're adding all these extras. So we could write this as, so at the nth stage, so what we'll do is an is equal to Sn minus 1. This is the previous stage, or previous sides. Number of previous sides, and then times it by an, new area added. This is the new area added. Yeah, so initially for the first construction, we're adding 3 triangles to the 3 number of sides of the original triangle. And then then this is going to equal to, well, we know the number of sides right here. This equals to 3 times 4n minus 1. And yeah, that is just from the above. Remember our formulas. So we had set up for part A. So Sn equals to r times 4 to the power of n. But we're looking at the previous one, so n minus 1. Then we'll put a Sn minus 1 is equal to 3 times 4 times 10 times n to the power of n minus 1. And the next one is an, that's just over here, that is a over 9n. And note here we can combine this 9n and this 3 because they both have the same factor, which is 3. So note right here, note 3 over 9, and this equals to, well, 3 over 3 squared. 3 squared to the power of n. That's just the same thing as writing 3 over 3. 3 over 3 2n. Again, it's all just power rules. And then now we can subtract this over. So we can write this as 3 to the power of 1. Move that downward, so it's equals to 1 and 3 to n minus 1. All right, so we have this, and then we could throw that inside. So this equals 2, and put the a in front, times 4n minus 1 over 3 2n minus 1. And so that is the area added at each subsequent construction. So each time you do the new Snowflake construction, you're adding area of this, which is a of the original, times it by 4 to the power of n minus 1, divided by 3 times, 3 to the power of n minus 1. Alright, so moving forward, so then the total area enclosed by the snowflake curve is, total area, we'll just write that as a. This equals to lowercase a is the original, so original triangle. So original triangle, and then plus a1, that is step 1. Step 1 triangles were added, then we're a2, and that is step 2, plus a3, plus dot dot dot, and again this is just dot dot dot. So we're good. That's to be step 3, and so on. And each step is this an that we're adding there. And I'll just write that here all the way, plus n, so the nth step there. Well, actually, we're not going to n, we're going to infinity, so it just keeps going on. I'll remove that an. So that's just, over to an, or you could just write an and then plus dot dot dot, etc. All right, so what this will equal to is equals to a is equal to lowercase a plus, and now a1, so that's n equals 1, we could put that in here. So when you have 4 to the n, to the a, or to the 1 minus 1, that's 4 to the 0, that's equals to 1. And then here, if you put a n equals 1 here, you'll have 2 minus 1. That's just 1. So that equals to a times it by 1 over 3, and then I'll just put a bracket here. This part is just the 4, 1 minus 1, over 3, 2 times 1 minus 1, which equals to 4 to the 0, over 3 to the 2 minus 1 is 1. It is 1 over 3. So that's just 1 over 3, like that. All right. And then the next setup is plus, and then when we have n is 2, this will be 4 to the power of 1. This will be 3 to the power of, this is 4 minus 1, that'd be 3. So this will be, again, another a times by 4 power of 1, 3 to the power of 3. And the next one's going to be a 4, and it's going to be 2, because when you put a 3 in, 3 minus 1 is 2. And this one, 3 times 2 is 6, minus 1 is 5. So notice the pattern now. 3 to the 5, like that. And then the next one is just going to be a 4, 3, 3, 7. So it goes every odd. This one is every single one, plus dot, dot, dot. And put this in a bracket like that. And notice what we have here again. This is another geometric series. And I'll show you that. So this is a geometric series. Whenever you have something increasing like this, where there's power 1, 2, 3, and then even this one is odd, but they're all in the same number. So it's 3, it's just separated by 2. So 3, 5, 7, etc. This is a geometric series. Geometric series. And what we could do is, well, let's just determine the terms. So this is, recall geometric series. We have a plus ar plus ar squared plus etc. dot 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 all the way until forever. Yeah, so in our case, what we have is, we have a, and then this is 1 minus 1 over 3. So we have a over 3. This could be our equivalent of our a, like this. So this could be our a. So that's this part right here. And then what we have is plus, and then, yeah, so that's our a. So a is multiplied everywhere. So notice how it's multiplied everywhere there, 1 over 3. So we'll put this a over 3 right here. And then the next term is going to be r. And this is going to be, well, 4 over 3 squared. So 4 to the 1 over 3 squared. And notice here, so 3 squared, this is 1, so these combine, so you'll have 3 to the 3, so that's just this one right here. And then the next one here, you can start seeing the pattern. A over 3 again, that's our a. And then this will be a 4 there. So then this would be a 4 over 3 squared again, but then squared there, so that the bottom is a 4. Is a 4 like that. So basically, we could just put this in a bracket, and you're seeing that this is actually the r value. And put it like that. Yeah, just fix that up and fix this up to 3 squared. Yeah, so notice here. So when you square this, you get a 4 squared. And this will be 3 to 3 squared. Squared will be 3 to the 4. But then you already took this out. Add those up, that'll be 3 to the 5. So in other words, r is equal to 4 over 3 squared. And let's just do one more here. A to the 3 times it by 4 over 3 squared to the power of 3. So then this would be 4 to the 3, and then 3 squared cubed, that'll be 3 to the 6 plus 1, 3 to the 7. So 3 to the 7, and there's 4 cubed there. Plus dot dot dot. Let's put a closed bracket like this, because we already have the regular brackets there. So now this one here, 4 over 3 squared is equal to 4 over 9, and this is less than 1. And remember our geometric series, if the absolute value of r is less than 1, it's convergent, like that. Alright, yeah, so this is a convergent geometric series, so now we can apply the formula for it. So using the formula for the sum of a convergent geometric series we get, and we already gone over it several times in this video, that's going to be a divided by 1 minus r. So then we get is the area, or the total area is going to equal to the original a plus, and then this is going to be our a minus 1 over r. So in our case, our a is our a over 3 divided by 1 minus our r, and our r is going to be our 4 over 9. So remember, this is our equals to our a in our formula, and this is our r in our formula. And I put this 3 lines for equals to say that this corresponds to it. It doesn't actually equal to a because we have an a here, just to show that we're not talking about this a. We're talking about this one here, so it just corresponds to. So what we'll do here is, multiply the top and bottom by 9. And here, just made that a bit more clear. And also, times by 9 on top and bottom, so we can do some cancellations. This will cancel, will just equal to a 3. This will just cancel, because 9 is just 3 times 3. And what we get is, and this is going to equal to, this will equal to a, and we're only doing it on this fractions, plus, then we'll have an a on top, and then this 1 minus 4 over 9, well, that's going to be 9, we're going to multiply it inside, minus 4. So that's just a 9 minus 4 there. Yeah, fix that up. So this would be 9 minus, minus 4, just like that. So then this equals to a plus a over 5. And forgot the 3 here, so we forgot this 3. So this is going to be 3a, and there's going to be 3a over 5, like that. So times this one here, times it by 5 over 5, what we get is, so this whole thing equals to 5a plus 3a, so we have the same common denominator of 5, equals to 8 over 5a. So that is our answer. Or put that together, 8a over 5. So that is our total area of the triangle. of the snowflake. And now we just need to solve for the area of the original triangle. And we could use a sine function, or we'll just use Pythagoras right here. So remember, these are equilateral triangle. Just do this for completeness. Draw this. Remember, and the sides were 1, 1. And then we have a 1 right here, and also the h right here. This is, let's go 1/2, 1/2. And we already solved h earlier, but we'll just do that again. Yeah, so h is equal to, well, let's just go over here. So the hypotenuse squared, 1 squared, equals to h squared plus 1/2, and then all squared, like that. And that just equals 2, and then we'll just solve it. H squared is equal to 1 minus 1 over 2 squared is 4, and then basically square both sides. So h is equal to plus or minus, this is 4 times 4, plus or minus, this is square root 3 over 4, like that. And here's move that over here, so this equals 3 over 4, square root both sides, and take the positive always, so it's going to be square root 3 over 2, because 4 square root 4 is just 2. And just for completeness, this one, I always do this 4 over 4, same common denominator, and that becomes that. So that is our h. So that's our h. And now we put that in our area formula. So a, or I'll put lowercase a because we're dealing with a equals to base times height divided by 2, which equals to base is 1. Base is 1. This is 1/2, and that was just for this Pythagoras. But base is b, like that. And move this away. And then then height is going to be, and this is divided by 2, square root 3 over 2. Yeah, that's our h. So then this becomes, just throw that in there. This becomes square root 3 over 4 is equals to a. like that. So that is the original area. Yeah, so the area enclosed by the snowflake curve is, and then this is 8a5. So total area is equal to 8a over 5, which equals to 8 over 5 times by square root 3 over 4. Like that. This cancels, be a 2, this cancels. And we're left with equals to 2 square root 3 over 5. Absolutely amazing. So we were able to solve the area of an infinitely long snowflake curve. All right. Yeah, so the solution manual just stops here, but let's go a bit further. So for further context, let's calculate the original versus snowflake areas. So the original a, lowercase a, is equal to square root 3 over 4, so that's over here. That area is equal to 0.433012, etc. Keeps going on and on. And this is just with my built-in calculator on OneNote, so equals the space like that. And then you could also do it over here. And then compared with the large area, or the total snowflake area squared 3 times 2 over 5, that equals to 0.69. And here's 0.69. And then the percent increase, so if you subtract the total area minus the original area, divided by the original, so we get a ratio, times by 100, you get 60%. Yeah, so it's a rounding error here, but it should be exactly 60. So yeah. Calculator gives this one 60%, 0.000 all the way to 112. And the percent increase, yeah, if I use the equations as opposed to the results of it, so there's less storing. And then if I do just go square root 3 times 2 over 5 minus square root 3 over 4. This is a, that's capital A, divided by the original a, and times by 100 equals to 60. Yeah, so there it is. It just if you right away press space, it automatically calculates. And this one all the way to 0.1 there, so it's slightly more accurate. But MES note, likely a calculation rounding error, since the exact answer is 60%. And there's a link to Wolfram Alpha. And yeah, so Wolfram Alpha calculator has it exactly that. And yeah, here, if I just go to Wolfram Alpha, so there's a link, click it, it goes to here, and you get this square root 3 set up here, times 2 over 5 minus square root 3 over 4. Then divided by square root 3 over 4, and then times 100, exact result is exactly 60. So yes, fascinating stuff here.